In this installment, we're going to look at motion and the forces involved in an elevator. This is a very commonly covered, dealt with, and considered topic in physics, and does show up on the AP fairly often as well. So the first thing I want to review before we do that is the force normal. The way we measure the force normal is to imagine we're standing on a scale. And inside a scale, there's a bunch of springs. And so when we step up onto the platform, the springs get squished. But you might imagine then also that if whatever the scale is on is moved upward, it would compress the springs too. So whether you step on something, it will compress the springs, or if you're standing on the springs and you move up whatever the spring or the scale is on moves upward, it will also compress the springs. So we're going to consider an elevator in 5 locations. We have a journey up and we have a journey down. We're going to start with a journey up, and we're going to start at the bottom. So at the bottom, our person is in the elevator and they are stationary. And then there's a period of time where they accelerate. And then there's a period where they're traveling at constant velocity. And then a portion of time where they're slowing down. And then when they are at rest or stationary at the top. So we want to imagine what the forces are involved in every one of these locations. Now, what we know is, since the distance between the center of the Earth and the person is not changing very much, that the force of gravity will be the same at every one of these locations. So we can put Fg, 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 and Fg. So in all of those locations, the weight of the person is the same. The gravitational force of attraction between the Earth and the person is the same at every one of those locations. Now, when a person is standing there stationary at the bottom, waiting to go, the scale reads a normal force equal and opposite to the force of gravity. The person is not accelerating. There's no acceleration going on at all. The forces are balanced. The acceleration is 0. When we look at the situation where it's traveling at constant velocity, well, again, there's a net force of 0. There's no acceleration going on, so we know that the normal force is equal there as well. So the question then becomes, what happens between these two when it's accelerating? Well, if the net force is upward, then the normal force must be greater. If there is a net acceleration upward, the normal force must be greater than the weight. So a person standing on that scale, and if we go back up to the top, look at our scale and imagine it, what's happening is the person standing on the scale and the bottom of the elevator moves up, which compresses the springs, makes it read heavy. So the scale reads and the person feels heavy. When they're stationary at the bottom, it's normal, and when they're at constant velocity, it's normal. When we consider the person all the way at the top stationary, we can see also again, since there is no acceleration, the force normal and the force of gravity will be equal and opposite to each other. And again, the scale will read normal. So what happens when it is slowing down? So if we look at our scale at the top again, we have the elevator and the person moving at the same speed. But what happens is the person is moving at a certain velocity, and due to the law of inertia, an object wants to keep its current state of velocity, but the elevator slows down. Since the elevator slows down and the person keeps going at the same speed, the springs elongate a little bit, which makes it light. So the person will feel light. And the force then, since there is acceleration, the acceleration is downward. The person slows from some velocity, some constant velocity, to 0. And in that case, for that to happen, the person is slowing in the upward direction, which means the net force is down. If we're slowing on the way up, the net force is downward. And so we can see in this case that the force of gravity is larger than the force normal. So this is the motion on the way up. We notice that there is this normal, normal, normal. And on the way up, when we're accelerating, it reads heavy. And we're slowing down on the way at the top, it reads light. Now let's take the downward journey. On the downward journey, well, we know the force of gravity is equal everywhere. Every one of these locations. And on the way down, we have the following events. We're stationary at the top, and then we speed up on our way down, and then we're traveling at constant velocity, and then we slow down, and then we are stationary. So stationary, we know the net force is 0, so the normal force and the force of gravity must be equal and opposite to each other. And when it's constant, in the middle of the journey, we also know the force of normal and the force of gravity will be equal and opposite to each other because the velocity is constant. There's no acceleration. And at the bottom, when we are stationary, again, the acceleration is 0, so the normal force is equal and opposite to the force of gravity. So the challenging part is to discern what happens in this initial motion. So here we are at the top, standing on our scale, and an object, the body, wants to always maintain its current velocity. And what occurs is the elevator drops out from underneath, which would elongate the springs and make it feel light. And lo and behold, we felt normal at the top, but when the bottom drops out, it reads light. The acceleration of getting faster is downward. We know when it's constant, we have a normal reading, and at the bottom we have a normal reading. But what about this instant between it being constant and it slowing down? So again, we can imagine our inertial elevator here, and at the bottom of this is the elevator floor, and we have the person has a certain velocity moving downward. It wants to preserve that state of velocity, but the elevator slows down, causing the springs to compress. And when it compresses, that means it reads heavy. And that means that if we're getting slower on the way down, that means the force causing that slowing down must be directed upward. So the net force must be upward, just like it was on the way up. So we see a net force upward. And if we go to the accelerating part, there is a net force downward and a net force downward. So this is not intuitive at all that this is the case. We can see here when we're stationary at the top, that's not a surprise that everything would be exactly the same. It would read normal, the forces would be balanced, there'd be no net force. It would be similar in the midpoint when we're traveling at constant velocity as stationary. Notice that the free bodies diagrams look the same. These are the same. In terms of the forces, there's no difference between an object with 0 velocity and an object with constant velocity. This is the difference between static equilibrium and translational equilibrium. The forces are exactly the same. And similarly, we see at the bottom, the third case, stationary forces in the normal weights occurring like so. But what is not at all obvious is that the scale, when we are slowing down on the way up, will read exactly the same thing as when we're accelerating on the way down. In other words, if you were in an elevator and you woke up and you knew you weighed 110 pounds, normally. But you look at the scale, you're on a scale, and the scale reads 105 pounds. You could not tell you could not distinguish between moving up going upward and slowing down, or speeding up on the way down. You could not tell. Those motions feel exactly the same, and the forces are exactly the same. And so it'll come as no surprise then, although it's very non-intuitive, that if we are accelerating on the way up, it will read heavy, but it will also read heavy when we're slowing down on the way down. So, again, if you were asleep and you knew your weight were 110 pounds, and you woke up in the elevator and you stood on the scale and you weighed 120 pounds, that's what the scale read, you could not distinguish between accelerating on the way up and slowing down on the way down. You could not tell. You could not even discern if you're headed up or downward, because they will feel exactly the same. And that is a tour of the forces on an elevator.